All right, so hopefully the internet's back again. Let's try this again. So we got two barriers with open apertures, one with a wide width aperture and one with a narrow width aperture. Notice that the wavelengths are meant to be about the same. Try to do my best with my drawings in Google. And then this diffraction pattern comes out the other side. I'm trying to show the constructive and destructive interference. See these gaps? That's supposed to be illustrating my destructive interference. But the idea here is, though, that when waves hit a wide gap, you end up actually getting a narrow distribution to the central bright region. And when the waves hit a narrow gap, the distribution actually gets wider, but it actually gets dimmer as well. And people say, okay, why dimmer? Well, isn't less energy getting through with the narrower gap? So dimmer, less pronounced. Why does it get wider? Remember what we said before, when you have a really narrow gap, the more rounded that diffraction ends up being. In other words, the more spread out it ends up being for a narrow gap, okay? Now, something we didn't talk about before was that there's actually a secondary bright region out there. So there's a primary, secondary, and tertiary, I should say, bright region. And the tertiary bright region's even dimmer than the secondary. And I'm sure that this is a language that's fallen away in terms of use. But can you guys see that it sort of reminds you of like a peaked hat with like a ripply edge around the edges? And this is also true when it's a pinprick, as opposed to a gap, like a single crack in a material. And so because of this graph, I've seen it written in a few places. They call it the Mexican hat, the sombrero distribution. And I'm sure that that's, for some reason, people are going to not like that. So let's just call it like a brimmed hat. But can you see how it would have like a peak in the middle where the head would go for a hat, and this sort of like brim that goes out the side, like a sun hat, right? But in terms of how we measure this stuff out, we actually talk about, I'll put in a dotted line here and a dotted line here, we talk about the width of the central bright region. So from here to here, from the lowest point to the next lowest point around the symmetry, that's the central bright region, call it the CBR. But then we also talk about from that dark point to the next dark point, that's how wide the next bright region would be. And what people have noticed is that the CBR, central bright region, is twice the width of the other maxima. So remember, these maxima are really bright stripes that are being projected onto a screen. And so we're saying that this bright stripe in the middle is twice as wide as the next bright stripe over on either side. And actually, each of the successive bright stripes are the same width as each other. Maybe we should say this is, because I said it out loud earlier, dimmer due to a narrower slit. But also wider. And so in terms of proportionality, what we could say is that as the width decreases, the spread of the interference pattern gets wider. As the width increases, the intensity of the waves coming out the other side gets higher. That could be a nice proportionality way to talk about this, okay? Anyway, the waves travel through a single slit, that's what we're talking about, and are projected onto a screen. The curve is a visual aid to indicate the relative brightness. So I tried to talk about that already. this curve that we're talking about here is really a brightness graph, essentially, where the vertical axis for this brightness graph is the intensity, and the horizontal is like spatial. And this W is the width of the slit, as I've said before out loud. And so here we could go back and we could label in the width of the slit as W. And for small angle radians, theta is equal to lambda over W. But for our purposes, we're going to avoid this, okay? I'm only putting this out there as something that you might encounter in the wild, wild web, that when you talk about theta values where the theta value is really, really small, there's an approximation that lambda over W is the ratio that's equal to theta. And here's what I mean by theta. If I take a point that's at the center of the width and I connect that point to a point on the graph where there's destructive interference, then that line segment relative to the principal axis would be called theta 1. That would be theta 1 for the n equals 1 value, and we're going to bring back integers again, for destructive interference. Of course, right here, there'd be an n equals 2 value for destructive interference, because remember, this is symmetrical, so that means that this would also be n equals 1, and this would also be n equals 2, because it's a symmetrical pattern. And we also use the same variable with two-slit interference, that the distance from the center of the source to the screen is going to be labeled as capital L for the path length. Something else I want to throw in here is that N is for nodal line, which means destructive interference. The bright spots are going to happen at what I'm going to call the M locations. So I could have an M equals 1. I could have an M equals 2 value. Maxima. Okay. And while I'm not going to go through the distribution equation calculation like I did for the two-slit interference, I'm going to say this. I'm going to say that for the first minimum, for the first dark spot, that's the n equals 1, I would say sine of theta 1 is equal to lambda over W. Oops, lambda over W. That's if we're using degrees. Notice that I'm differentiating between radians and degrees, and we're going to use exclusively degrees. Another thing that I could say is that lambda is equal to W times, oh shucks, I'm going to have to come up with a new measurement. From here to here, from the center to that first dark spot, I'm going to call that the Y1 value. And I'm going to call the distance between successive dark spots the delta Y value. Just giving names to measurements. So now I'm going to say lambda is equal to W times Y1 over L. Now notice that since the central bright region is twice the width of all the other bright regions, Y1 is going to be the same value as delta Y. Right? Because Y1 is from the center out to that first dark spot, so it's half the width of the central bright region. Which means that Y1 equals delta Y, which means that if I'm going to make this claim here, then I could also state it as lambda equals W times delta Y over L. Let's just let that sink in for a second. Those two equations mean the exact same thing, because since the central bright region is twice the width of all the other bright regions, Y1 and delta Y would be the same value. What's Y1? Y1 is how far away that dark spot is from the center of the pattern. You'd measure it in meters. Okay? Does anybody have any questions about that? Does that make sense? I'm just laying out geometry and the letters and what the letters stand for. Okay? You know what? Let's make it more visual, just to make sure that nobody gets lost on this. If I was drawing this distribution pattern, this brightness distribution pattern, let's make sure we got this. I've got my central bright region. I've got another bright region, another lesser bright region. See the brim of the hat. Measuring from the center outwards to the first dark spot, I would call Y1. From that dark spot to the next dark spot, delta Y. From the center out to the second dark spot, what do you think I'd call that one? Y2? Call Y2. Okay? All right. So with that in mind, I want to say, oh, okay, well then there must be some integer multiple thing going on here. Sine theta n, where n is the dark spot that we're talking about as an index, is equal to n times lambda over w. In other words, the theta value that corresponds to the n1 or the n2 could be calculated using this equation. And likewise, the theta value that would be associated with a bright spot, I'm going to call it theta m, would be equal to m minus 1/2 lambda over w. And just like we had in two-slit interference, we had an equation that was for destructive interference and an equation that was for constructive interference. So we do again for single-slit interference. Now, in terms of the coding of this, well, why would I want to have this equation and this equation? Well, hey, take a look at this equation. This equation makes use of a relationship that doesn't involve the theta values. You see what I mean? I could relate how far away a dark spot is from the center to the width of the gap, the distance from the gap to the screen, and the wavelength. I said earlier that we could use this for materials testing. If I know what the wavelength of my laser is, and I can measure how far my crack in a material is from a screen that I'm projecting onto, and I can measure on the screen how far away the first destructive interference is from the center of the pattern, then that means I could calculate how big the crack is in my material. This could be a materials testing thing, okay? That's a great use for this. In terms of making sure we got what all the subscripts are all about, notice that I've been really intentional to say that N is for the nodes. Nodes mean dark spots. The M integer is being used here for the bright spots, the maxima, maximum brightness. When I talk about dark spots, people in textbooks will often talk about the minima. When I talk about bright spots, people in textbooks will often talk about fringes. Okay, so we have bright fringes, we have dark nodes or dark minima. And basically that amounts to being bright stripes and dark stripes being projected onto a screen. But a little bit of vocabulary unpacking, okay? And what I found is that some textbooks aren't entirely consistent with that vocabulary. So if you have a doubt, just ask me. Our textbook's pretty good about it. I think there are a couple of typos in there, and we can navigate that, okay? It's not a problem. If it's a test, then I'll be sure to state it as a dark node. I'll double emphasize it by using both vocabulary words so that we take out that ambiguity, okay? And if you're a casual reader or you knew what you were talking about, you'd be like, this guy's really redundant in his writing. But I would be doing it to make sure that I'm really driving home that we're clear about what we're talking about. All right, so the distance, y1, is useful for finding the width of the CBR. And that's because the width of the CBR is equal to 2 times y1. And to make sure there's no doubt about it, y1 is the distance from the center to the first node. center of the CBR to the first node. And I'll put in brackets just so that we're doing proper word association here. The first node, or dark spot.